Day, ma'am. Today I will be explaining the low frequency response to BGT amplifier. So, BGT amplifier contains three important capacitors. First is the input coupling capacitor, or the CS, emitter bypass capacitor, or the CE, and the output coupling capacitor, or the CC. So, at high frequencies, these capacitors act almost like short circuits, so they have little effect on the amplifier. However, at low frequencies, their reactance increases. This means they oppose the flow of AC signals more, causing the amplifier gain to decrease. Because of this, each capacitor creates its own lower cutoff frequency. Now let us move on to the formula of cutoff frequency due to the input capacitor, or the CS. So the formula is F sub Ls, which you can see above, or yes, in the picture, is equal to 1 over 2 pi Rs plus Ri times CS. So this formula comes from the RC circuit basic equation, which is the FC equal to 1 over 2 pi RC. So RS is the source resistance and the RI is the input resistance. So in the R from the original formula will be kanang ilisa nato og RS plus RI, which then gives us the formula that we will be using, which is the F sub Ls is equal to 1 over 2 pi times Rs plus Ri times Cs. So Ri is the input resistance, is equal to R1 parallel to R2 parallel to beta Re, or Re is the small emitter resistance. So next is the cutoff frequency, or the formula of cutoff frequency due to the bypass capacitor. So it is the F sub Le 1 over 2 pi Re times Ce. It also comes from the standard RC cutoff equation, which is Fc is equal to 1 over 2 pi Rc. So Re is equal to yes, the little Re from the above the kanang makita mo sa picture is equal to Re with dako nga E is parallel to Rs over beta plus Re, which is both small letter. So Rs is the equivalent resistance seen from the base, and it is equal to Rs without apostrophe, and Rs parallel to R1 parallel to R2. So why nganong kani nga equation? It is because the bypass capacitor is connected across the emitter resistor, which you can see on the figure or on the picture. Now let us move on to the cutoff frequency due to the output capacitor. So it is, the formula is F sub Lc equals to 1 over 2 pi times Ro plus Rl times Cc, or the output coupling capacitor. So it also comes from the RC cutoff frequency formula, and as you can see, the resistance seen by the capacitor is Ro plus Rl, and the output resistance, makita niyo din sa figure, is Ro plus Rc parallel to the small Ro. So the Rc is the collector resistor, whereas the Ro, the smaller Ro is the internal output resistance of the transistor, and Rl is the load resistor. Now to the D, which is give one example of a BGT amplifier solving for cutoff frequencies due to input, output, and bypass capacitor. So with our example 9.11, determine the cutoff frequencies for the network using the following parameters. So coupling input capacitor is equal to 10 microfarad, R1 is equal to 40 kilo ohms, RL is equal to 2.2 kilo ohms, beta is equal to 100. Um, the emitter bypass capacitor is equal to 20 microfarad, R2 is equal to 10 kilo ohms, and the output coupling capacitor is equal to 1 microfarad, and the RE is equal to 2 kilo ohms, and RC equal to 4 kilo ohms, with RO equal to infinite ohms and VCC equal to 20 volts. So first is we have to determine the RE for DC conditions. So we first apply the test equations, which is beta times RE is equal to 100 times 2 kilo ohms is equal to 200 kilo ohms, which is that's yes, of 10 R2 is equal to 100 kilo ohms. Since this is satisfied by the DC voltage determined by VB approximately equal to R2, VCC equal to R2 plus over R2 plus R1 is equal to 200 volts over 50, and thus VB is 4 volts. And IE is equal to, with the formula, VE over RE, and we have the result of 1.65 MA, and the RE we have 15.76 ohms, and then the beta times RE is equal to 100 times 15.75, which is 1.575 kilo ohms. Now to the mid-band gain, which is AV equal to VO over VI, or also equal to negative RC parallel to RL over RE, with equal to negative 4 kilo ohms parallel to 2.2 kilo ohms over 15.76 kilo ohms, and thus we have approximately negative 90. And so for the input coupling capacitor, we have Ri is equal to, with our formula earlier, which is the R1 parallel to R2 and parallel to BRE. We have our 1.32 kilo ohms. Now we substitute that into our formula. We have F sub Ls is equal to 1 over 2 pi times 1.32 times 10 microfarad. We have F sub Ls approximately equal to 12.06 hertz. Now let's move on to the output coupling capacitor, which has a formula of F sub Ls is equal to 1 over 2 pi times RO plus RL times CC, with RO is equal to RC parallel to RO approximately equal to RC. So we input those values, which is 1 over 6.28 times 4 kilo ohms plus 2.2 kilo ohms times 1 microfarad, and then we have the final answer of 25.68. Now for our RE is equal to RE parallel to R1 parallel to R2 over beta plus RE. We input the value 2 kilo ohms parallel to 40 times 40 kilo ohms parallel to 10 kilo ohms over 100 plus 15.76, and thus we have 19.38. So we substitute that into our formula, which is F sub Le is equal to 1 over 2 pi Re times Ce. So this again, this formula is for our emitter bypass capacitor, and so we have 1 over 6.28 times 91.38 ohms times 20 microfarad, and such we have 87.13 hertz. So our final answer for the input, output, and the emitter capacitor are 12.06 Hz for the input, 25.68 Hz for the output, and for the emitter we have 87.13 Hz. Lastly, determine how to solve for the dominant frequency. So the dominant frequency in a BJT amplifier is the cutoff frequency that has the greatest effect on the amplifier's overall frequency response. So the steps in determining the dominant frequency is, first, we have to calculate each cutoff frequency caused by the input coupling capacitor, emitter bypass capacitor, output coupling capacitor. Second is we have to compare the three values, and lastly, the highest cutoff frequency is the dominant frequency. So that's how you will determine the dominant frequency. That's all.